We're here to talk about zwitterions today. Zwitterions comes from a word that means hybrid. We've drawn amino acids like this so far with the carboxylic acid. Because the amino part is basic and a carboxylic acid is acidic, these molecules typically exist in a form where the amine end has a positive charge and the carboxyl end has a negative charge. So if I'm looking at this overall, this is still neutral, but now my carboxylate has been deprotonated and my amine has been protonated. And we know that this makes sense because an amine is a base and a carboxylic acid is an acid, and it exists in the same molecule. So typically your amino acid is going to look more like this than like this. Amino acids are salts at room temp. They are solids at room temp, and you can put them on the shelf. They're stable. They have very high melting points, and so that's sort of physical evidence that these are going to be salts. Salts typically have very high melting points. So a zwitterion is a molecule that has an equal number of positive and negative charges. So it is neutral, but it does have charges. Our amino acid, depending on the pH it's in, is going to have potentially a positive charge or a negative charge. So if I'm thinking about my zwitterion here, and if I'm thinking about that in various pHs, so if I have a pH scale here, and I have a neutral pH of 7 here, and then I have a pH like 1 or a pH of 14. This would be something that's acidic with a pH of 1, and a pH of 14 would be very basic. pH of 7 would be neutral. So I can think about my zwitterion having a different form depending on the pH. In the neutral pH, I can think about the zwitterion being formed here, where the amine part has a proton and the carboxylate has been deprotonated. But if I go more acidic, then essentially everything that can have a proton is going to have a proton. So what I'd have here is the amino part that has a positive charge, but I'd also have my carboxylic acid again. And if you're looking at this, we have a positive 1 charge here, and then the carboxylic acid has no charge. So the overall charge of this side is going to be a +1. If I look at the other side, if it's basic, then that essentially means anything that can be deprotonated will be. So my carboxylate will have that -1 charge, and I'll have my R group, that's we're going to say is neutral for now. And then that proton will be removed from the amine group, so that will no longer have a +1 charge. But my carboxylate will have a -1 charge. So overall, this is going to have a -1 charge. Depending on what pH you're in, you're going to have one of these three forms. You're either going to have the protonated form in acidic solution, or you'll have the neutral form, the zwitterion, in neutral solution, or if you're in a basic solution, you might have a -1 charge. So when I'm thinking about the isoelectric point, I sort of talked about the isoelectric point a little bit before. If an isoelectric point is, let's say, like over here, it's 5 to 6, then if I am below 5 or 6, even pH 4, I can imagine that I'm going to be the protonated form. If I'm above the isoelectric point, anywhere above that 5.1 to 6, even 8, I'm going to have the fully deprotonated form. So I can predict what type of form I'm going to have based on the pH of the solution. We're going to talk about peptides. Peptides are amino acids that are bound together. So a peptide is formed by, a dipeptide is just two amino acids. So we have the backbone of the amino acid right here, and then we're going to have an amide bond between a carboxylate group of one amino acid and an amine of the other amino acid. When we think about how these molecules are put together, um, we can think about having the nitrogen N on one side, then that's attached to a carbon, that's my carbon alpha. Then I'm going to have my carboxylate end. So that would be amino acid 1. Then I'm going to think about making a bond to another amino acid. Another amino acid would make an amide bond between this carbon atom and the amine end of the second amino acid. So I'm just going to draw carbon alpha and then the carboxylate end. When we put these amino acids together, you sort of notice that you always have an N on one side and you have a C on the other side. So we think about amino acids or peptides always being written from the N to the C terminus. That just means from the amine N to the carboxylate end. So it's always going to be from the N to the C terminus. When I'm thinking about dipeptides, di means 2, tri means 3, tetra means 4, penta means 5, hexa means 6. So I can have dipeptides, tripeptides, tetrapeptides. These are going to be oligopeptides. Once peptides get really big and a bunch of them are put together, that's going to be called a polypeptide. Polypeptides form into proteins. So we start with amino acids, they form peptides. Peptides form polypeptides, those fold into proteins, and we will talk about that. So again, the N terminus is always going to be on the left side of the molecule, and the C terminus is always going to be on the right side of the molecule. Let's recall again that every time we put an amino acid together, let me just draw one here. And I'll draw another one. In fact, let me draw this in a different color. Sorry about that. Whenever I form an amide bond here between the amine group and the carboxyl group of another molecule, that's going to form an amide bond. So the nitrogen part is going to attack the partially positive carbon atom there, and we're going to form an amide bond, and we're going to lose a molecule of water when we form that bond. So let's call this R prime. When I put this molecule together, I'm going to keep the colors the same here. There's my R prime. And then I have my C terminal. So the amide bond is right there between the carbon and the nitrogen. And again, that's why I drew this initially as an abbreviation of N, C, C, N, C, C. My amide bond, again, is right there. We sort of already went over all of this. I'm going to skip this slide. The amide bond, because it has this carbonyl, we have resonance with this bond. So I'm going to draw here the resonance form for this molecule. Remember, I have a lone pair of electrons on this nitrogen, so I can draw a resonance form here where I move those electrons to make a bond with the carbon, and I move the double bond electrons from the carbon to the oxygen, carbonyl, to the oxygen. So the form that I make will be this. The amide bond, again, is right here. So this is a resonance structure, and I'm going to say, remember, we draw resonance structures with the double-headed arrow. Because I can draw this resonance structure, when I think about my carbon atom right there, I think most of you hopefully by now know that this would be an sp2 carbon. Bond angles would be 109.5. The nitrogen atom here would be a trigonal pyramidal carbon. It would be sp3 hybridized and bond angles less than 109. But when I look at the molecule below, what I'm noticing is that now the nitrogen looks like it has a lot of sp2 character because it is involved in the double bond. So this is more like an sp2 hybridized atom, and my carbon still is sp2. This bond is relatively planar, and it is also a very strong bond. So the transplanar nature of the peptide bond accounts for high melting points and high boiling points. Additionally, in an amide bond, because that nitrogen is tied up in this resonance structure, the nitrogen that would normally be fairly basic, so remember, amines are basic, but amides, not basic. The lone pair on the nitrogen is now tied up in this double bond character to the carbonyl, and so the amide bond is no longer basic. So here's a nice ball and stick model of an amino acid. I have the N terminus here. There's a carbon atom. This is my alpha. Then I have the carbonyl carbon. That's attached to another nitrogen from the second amino acid. Then I have an alpha carbon. And then I have the carboxyl end. When these molecules form, again, you're going to form water as a side product. because we always draw our peptide bonds from the N terminal to the C terminal, when I abbreviate these molecules, or when I abbreviate this tripeptide, I'm going to abbreviate it as alanine, glycine, serine, ALAGLYSER. When I put these together, I'm going to put these together. And you can go ahead and pause the video here if you want to make sure that you draw this correctly, but I will draw this out for you. So I have the serine end, and I'm going to draw this as a line bond formula because I don't like the condensed structural formula, and I think most of you feel more comfortable with line bond as well. So I'm going to draw that. The carboxyl group, you can abbreviate like this. You can also draw it out specifically like this. You can sort of do that however you want. Oops, I'm supposed to not have the nitrogen there, but I can't erase here, so just know that this hydrogen's not supposed to be there. You should be able to draw a dipeptide if you're given 2 amino acids, and the name of this would be SER, THR, that's serine, and threonine. So again, you do not have to memorize the amino acids. You do not have to memorize the 3-letter abbreviation for the amino acids, but you should be able to do a problem like this where you put the 2 amino acids together. Again, so for this one, you should be able to draw the bonds here. And let me go ahead and do that. I'm going to draw the molecule just like it is, even though normally we'd have the zwitterion form. And I'm also going to draw my water molecule. This one is alanine. This one is leucine. So when I write out the name for this, I'm going to write ALA-LEU. You should be able to match a structure like this up to a chart of amino acids. This one looks a little messy. Let's see. So when I'm looking at this, I have amino acid number 1 there, amino acid number 2 there, amino acid number 3 there, and amino acid number 4 at the end. And I am looking at a chart myself because sometimes I forget the structure of all of these. This is methionine. This is alanine. This is leucine. This is also alanine. Heads up, as I'm looking at this, there's probably supposed to be 3 hydrogens there and not 2. I'll have to fix that later. If I am drawing the so this is a tripeptide. And this is a tetrapeptide. Again, I encourage you to go ahead and try to do all of these on your own. Look up the structure of leucine, asparagine, and alanine, phenylalanine, glycine, glutamine, and valine, and put these together. I will do them. Let's see, I don't really have a lot of space there, so leucine, it kind of helps if you write all the amino acids first. So I'll write out leucine. Oops, somehow I ended up with pencil. Asparagine is one of the acidic amino acids. Alanine just has a methyl group. And then I'm going to go ahead and put these together. Oftentimes you will see the bonds like this. So the first R group is going to be like this. Second R group is going to be like this. And that's sort of so you can maintain a straight structure when you're drawing these. You don't have to do that. Do it as well as you can. But typically this is how we end up drawing them. So let me highlight here. This is amino acid 1. This is amino acid 2. Now I'm going to draw the nitrogen of the third one. So there we have leucine, asparagine, and alanine. At the bottom, let me sort of draw a line here. For my tetrapeptide, I'm going to draw phenylalanine. This one has a benzene ring. This one's aromatic. I'm going to draw glycine. Glycine is interesting because it is the only amino acid that is not chiral. We haven't really talked about the chirality too much here, but notice for the other amino acids, all of them have 4 different things attached at that alpha carbon. So the alpha carbon is chiral. Glycine, on the other hand, has just 2 hydrogens. So glycine is kind of special because it is not chiral. Then I want to draw glutamine, and kind of running out of space here. Glutamine is one of the ones that has the amide on it. And then we'll draw valine. That one has the isopropyl. And you can put all of these together, and I'll go ahead and do that down here. Hopefully I have enough space. Here's my carbonyl. Let me just erase that and make it a line bond. There we go. This is my nitrogen. So again, first amino acid, second amino acid, glycine, a very simple one. Oops, draw that as a line bond. There we go. So there's glycine, and now I'm going to attach that to glutamine. Carboxyl end of glutamine. Let me put a little squiggly here. So there's my phenylalanine. There's my glycine. There's my glutamine. And let me draw the last one, which is going to be my valine. Isopropyl there. And I'll draw my little squiggly for you. And here's valine. So there is the tetrapeptide. We are going to stop here for this video because it's starting to get a little bit long, and I will upload this, and I hope this is helpful.